Welcome to this explainer. Today, we're going to distill some truly fascinating insights from Chapter 14 of the book Making IT Sustainable to unpack a massive modern technological paradox. We're looking at how quantum computing acts as this incredibly powerful climate solution, but at the same time presents a totally unique sustainability challenge all on its own.
So, let's dive right into this big question. On one hand, we've got a technology so advanced it can solve complex environmental issues that our current classical computers simply can't touch. But on the other hand, it requires an absolutely enormous amount of energy to actually function. It's a genuine paradox, right? And understanding this dual role is absolutely crucial for the future of green tech. To unpack all of this, we'll start with the promise of quantum's climate solutions, then look at the paradox of its energy problem. From there, we'll explore the path forward with greener hardware, dive into sustainable quantum software, and wrap up with ways you can deepen your knowledge on the topic. Let's kick things off with Section 1, the promise of quantum's climate solutions. Okay, we are talking about tangible, real-world applications here. For instance, researchers at Microsoft and ETH Zurich actually used quantum algorithms to simulate a ruthenium complex. And why does that matter? Well, it helped identify efficient catalysts that can literally turn harmful CO2 into methanol, which is a super useful fuel and solvent. Quantum algorithms are also incredibly good at simulating complex fluid dynamics, meaning we get vastly improved, highly accurate advanced weather forecasting. To put that into perspective, classical computers, processing everything in basic binary zeros and ones, they quickly hit a brick wall when dealing with complex molecular interactions. But quantum computers use qubits. As highlighted in a really insightful IBM article on quantum advantage, this shift allows us to simulate properties right down to the atomic level. This is exactly what's helping companies like IBM and Daimler AG design EV batteries that are lighter and denser than we've ever seen before. Which brings us directly to Section 2, the paradox, also known as the quantum energy problem. Here's the catch. Qubits are unbelievably delicate. To maintain their quantum states without any environmental noise or experiencing what's called decoherence, quantum computers require these massive, energy-intensive dilution refrigerators. We are talking about cooling systems running near absolute zero, literally colder than the vacuum of deep space. These systems consume a staggering amount of power, and they generate their own heat that then has to be dissipated. So if we aren't careful, the energy required to run these climate-saving algorithms could end up contributing heavily to the very carbon footprint we are trying to reduce. Let's move to Section 3, the path forward, and how we're building greener hardware. The good news is, engineers are aggressively tackling this cooling problem from a few different angles. First, we have superconducting qubits, where recent advancements in materials science are allowing them to operate at slightly higher temperatures, which cuts down on cooling needs. Then there are silicon-based qubits. These leverage a superabundant material, though we do have to keep an eye on the environmental impact of manufacturing them. But one of the most fascinating approaches is diamond-based quantum computing. Diamond is highly inert, meaning it effectively isolates the qubit from noise and holds its quantum state longer using what's known as a nitrogen vacancy defect.
And then there is photonic quantum computing. This is a real game changer. By utilizing photons, actual particles of light, for computation, we can completely bypass the need for those energy-guzzling cryogenic cooling systems we talked about earlier. Because photons generate way less heat, these systems can often operate at room temperature. It's a true green alternative emerging in the quantum hardware space. Now, hardware is only half the battle, which leads us to Section 4, sustainable quantum software.
Just like in traditional IT, software design absolutely matters. We are entering this incredible era of verifiable quantum results, but getting there sustainably requires 4 main steps. First up, algorithmic efficiency, making sure we use fewer computational resources from the get-go. Second is error correction, which mitigates noise. Now, that's a delicate balance because error correction actually requires additional qubits. Third, we have resource management to optimize the allocation of those qubits and minimize energy use. And finally, hardware-aware programming ensures the software is adapting directly to the specific constraints of the machine it's running on. By doing all this, developers minimize the computational power needed to get accurate, verifiable results.
Today, the most practical solution we have in our toolkit is hybrid quantum classical computing. Instead of using a highly energy-intensive quantum computer for every single step of a problem, hybrid models offload tasks. They use classical computers for the basic everyday computations, and they reserve the quantum power strictly for the heavy lifting where it actually holds an advantage. Open source frameworks like IBM's Qiskit, Google's Cirq, and Xanadu's PennyLane are pioneering this entire space, and they're saving massive amounts of computational waste and energy in the process.
Finally, Section 5. Deepen your knowledge.
Because at the end of the day, this dual role of quantum computing as a climate savior that desperately needs its own energy diet is just one single piece of a massive puzzle in our pursuit of a greener digital infrastructure. From massive data centers to AI, the entire IT industry is undergoing a serious green revolution. A true sustainability strategy literally has to be integrated directly into operational and financial plans. It can't just be an afterthought. To master these techniques across all IT sectors, I highly recommend checking out Making IT Sustainable by Mikhail Glukhovtsev. It goes so much deeper into the technical frameworks and real-world applications that are shaping responsible technology today.
So I want to leave you with this final thought to ponder. As quantum technology scales exponentially, are our sustainable innovations going to evolve fast enough to ensure its climate solutions outpace its carbon footprints? It really is a race against time. Keep learning, keep asking those big questions, and I'll see you in the next explainer.